right, students, here we are looking back in section 4.9 from your syllabus, and now we're looking at cyclic groups and generators. And notice that the proof that all cyclic groups are abelian is also part of your syllabus. So we'll start by defining cyclic group. So any group that has elements that can be represented with a single element is a cyclic group. So if we think about the rotations of a triangle, of an equilateral triangle, so remember we had our equilateral triangle, and there's 3 different rotations that can happen. R0 is when we don't rotate it at all, so that's the 0-degree rotation. R1 was a 120-degree rotation, and R2 was a 240-degree rotation. Well, I can't represent R1 with R0 because R0 is just not rotating at all. But I can represent R1, obviously, as R1. R2 is the same as if I do rotation 1 twice. So remember, I can write this as R1 power of 2. It's not squaring it, it's doing the operation twice, so doing this rotation twice. If I do the rotation a 3rd time, I get back to where I started, 3 times 360 degrees. So notice I can write all of these rotations using the R1. So we call R1 a generator for this group, and since we can write all the elements in terms of R1, it's also a cyclic group. So R1 is a generator, and the group is cyclic. So cyclic groups have to have a generator, and that we can write all the terms as Rn. Notice that our group has an order of 3. Also, our generator element had an order of 3, and that must happen. Just because we have an order same as the group, though, does not make it cyclic.